name is Alexandra Touzeau, and I'm a postdoc at the University of Bergen in the team of Harald Soldman. And today I'm going to talk about stable water isotope observations during INTAROS cruises north of Svalbard. And more specifically, I will talk about links between isotopes and atmospheric circulations and sea ice processes. And this is now a nice view of Svalbard as we were moving northward. First, I would like to present delta 18O and the term excess that I will use throughout this presentation. Delta 18O is a common notation for describing the ratio between the heavy water molecule H218O compared to the common light molecule H216O. As you can see, to obtain this notation, we use first the ratio in our sample that we compare to the ratio in a reference. Here for water, the reference is the standard mean oceanic water, SMO. So we do air 18 sample minus air 18 SMO, and then we divide by air 18 SMO, and we multiply by 1000, otherwise we get a very, very small value. Therefore, delta 18O is expressed in per mil unit. A similar expression called delta D exists for the ratio between HDO and H216O. The delta D and the delta 18O of a water mass can be related together using the last equation on this slide, the red one. So the term excess is equal to delta D minus A delta 18O. So this is the second parameter that I will use. Why do we go out in the Arctic to measure isotopes? This is because isotopes have long been known to contain climatic information. They can be useful for reconstructing paleoclimate or also for improving the current climate models so that they can give better future climate projections. However, the isotopes do not vary only at long time scales. They also vary at shorter time scale, and in particular together with the natural water cycle. Here we have a focus in this study to measure isotopes in the air, in the vapor, and to look at the variability with different air masses, different air origin, as the wind is shifting from one direction to another. This study is also particular in that we provide rare information from the interior of the Arctic, a region where there are no permanent stations, because it is sea ice frozen and difficult to access. You need a ship to go there. We plan to make the information available through a database so that it can be used later by climate modelers for model development as constraint for model evaluation, for instance. Our campaign consisted in 2 INTAROS cruises, one in 2018 and one in 2019. The 2018 one is in red on the map and was including a part to the west of Svalbard and a part to the north of Svalbard, whereas the 2019 campaign mostly occurred in the northeast of Svalbard and all the way to the North Pole. The cruise took place on the Coast Guard vessel KV Svalbard, and on board we had an instrument for vapor measurement associated to an inlet outside. We were also taking regular samples of seawater, of precipitation, either snowfall or rainfall with this plastic box, and we were also taking sea ice core in the second field campaign, as well as snow at the surface. Here I present the result of delta weighting calibrated for each sample type. In red is snowfall, in green is the snow that was taken at the surface of the sea ice, in yellow is the rainfall, in blue is the sea ice sample, and in black is seawater. As you can see, we collected a lot of seawater samples during the first campaign and a lot of sea ice samples during the second campaign. And both sea ice and seawater have delta weighting values very close to 0, very tightly centered, whereas for the other samples we got really low values, really depleted values between -20 and 0. However, for sea ice, We have a small contribution from the snow at the surface, which was melting and percolating inside the sea ice, and therefore we get also some negative values, especially in the first centimeters of the sea ice. Here I present the results for delta weighting and deuterium excess in the vapor that was measured continuously during the campaign. For the left panel we have the 2018 campaign, and for the right panel we have the 2019 campaign, and delta weighting is at the top, deuterium excess is at the bottom. For the 2019 campaign, there was first quite high delta weighting values until the 8th of August, and then there were large variations in delta weighting with 3 periods with very low delta weighting values around the 13th and 23rd of August and around the 3rd of September, which are highlighted with red circles. These periods also correspond to quite high deuterium excess values, around +15. Here we make the hypothesis that the large variations observed both in delta weighting and deuterium excess are related to changes in the air mass trajectories, so the origin of the air is probably different, and in order to test this hypothesis we were building trajectories for the 23rd of August, which is a minima in delta weighting, and for the 29th of August, which is a maxima in delta weighting. We can see immediately that the trajectories for these 2 days are very different. These trajectories were built with the FlexPath tool, and for the 23rd of August we observe that most of the trajectories seems to come from the Canadian Arctic, from the west of the ship, whereas for the 29th of August most of the trajectories come from the south, and particularly from the Atlantic Ocean. Here we have zoomed in on the second part of the CARTEX campaign, the 2019 campaign. We have again in blue the isotopes in the vapor, and we have added in red and in yellow the isotopes in the snowfall and in the rainfall. We can see that for the snowfall, the delta weighting values closely follow the delta weighting values in the vapor, even if there is a shift. Which is normal due to equilibrium fractionation between the vapor and the precipitation. We can see that rainfall usually corresponds to the periods with quite high delta weighting values, and snowfall to periods with quite low delta weighting values, which would be coherent with the arrival of cold air from the Arctic. The deuterium excess has also values that are very similar in vapor and in precipitation, and this is again coherent with equilibrium precipitation. As a summary, we have seen that for the water samples we can divide them into 2 categories. In the first category are the sea ice and seawater samples, which have compositions that are very close to the one of the snow, so delta weighting values very close to 0. And on the other side we have the precipitation and the snow on ground, which were very depleted, between 0 and -20. We have also seen that the sea ice samples are partly depleted, and this corresponds to a contribution from precipitation, from the snow on ground that was melting and that was percolating and refreezing inside the sea ice, especially in the first layers of the sea ice. We have also seen that there is a link between the isotope composition in the vapor and the air mass trajectories, and we have seen in particular that there is higher deuterium excess and lower delta weighting in the vapor when the air is coming from the northwest and from the Canadian Arctic. We have also seen that there is a good relationship between delta weighting in precipitation and in vapor, and that the day excess are similar for the 2 phases of equator, and this is coherent with precipitation occurring at equilibrium during the cruise. And with this, I thank you very much for your attention and hope we can talk together more during the chat section. Goodbye, thank you.